we now know a color image, each pixel has three values, those three stacks of R, G, and B values. And I've made a, a yellow bar across this. This is a blepharisma. And what we're going to do is look at that line, maybe about 50 pixels across. So it's all the same Y value, but now we're moving in X. So here's X as we're going across that yellow line. And we're going to look at the values of each channel, the RGBs. The higher it is, the more red. And usually if they're usually in sync. So these are the three values for the red, green, and blue channels. And X is the horizontal, the pixels. When you convert this to gray, as I mentioned, the simple way is just you average these. You sum them all up and divide it by 3. So let's say we did that here. So this is now showing you the intensity as a function of X, the pixels. And what this hard thresholding does is you set a value, and if it's above the threshold, you consider the pixel is white, and if it's below the threshold, it's black. So that's how you binary quantize. And what the blurring does is basically average it. You notice this peak is going down. Oh, here's a good example. See this peak, it crossed over. If you averaged it, it would have been a little smoother, and that wouldn't have popped up and crossed the threshold. So that's why smoothing, averaging reduces those holes you'd see, and this would appear as a hole in the object. Okay, so this hard threshold does this quantization. The only thing that's a little confusing for us is our background is white, our objects are black. So if we did this thresholding like this, all the background would be white and our objects would be black. And OpenCV wants objects to be white and background to be black. So all we did when we called the quantization threshold function, we told it to please invert the results. So it did this thresholding, and then it just inverts this. So now it'll make wherever it saw black, it would switch to white.